Hey guys, so let's talk about these graphs a little bit and try to understand how we can use them to find slope. So first thing that's necessary is to see that there's a difference between these graphs here and these graphs here. These graphs here are all using the same y-axis. They're all using concentration, and then they're plotted against time. So that's why they look different. So these graphs here, one is concentration versus time, but this one's ln of concentration versus time, the natural log. And then this one's 1 over concentration versus time. So when we see that these are all linear, we think, oh, but if they're different integrated rate laws, why do they look so similar? Well, the reason they look similar is because the y-axis has been adjusted, and therefore these are not showing the same rates of reactions in terms of exponential growth of the rate, if that makes sense. So let's go ahead and try to show what I mean. So here in the zero order reaction, we see that if we look for the rate, because this is concentration versus time, so it's always going to show rate, we see that the rate is always equal to K, just like this equation shows. Anywhere along this graph, no matter how the concentration goes up, nothing really changes the rate. And that's why we say the rate is equal to a constant. Now here, our rate, this is the rate, right? It's no longer equal to just K, it's equal to K times A to the first order. So this means as we go up in concentration, or I guess in this case, it'd be easier to look at it as it's going down in concentration, we have a curved like journey, which means that if we had like 2 moles of something and then we reduced it to 1, the reaction would also have its rate divided by 2, just like the concentration did. So that's why it's curved, because the rate when it's at 2 here is not going to be the same as the rate when it's at 1 here. And then in our second order, we have an even higher exponent that it's raised to. So if you divide by 2, you would actually be left with a fourth. So let's do that. If there's 2 here, about here would be about at 0.5, which is a fourth of 2. So it's just steeper, that's it. And that's all you have to be able to recognize, is that these are exponential decay or exponential growth, okay? Now let's go on and try to find the slope. So we cannot use a graph that just has concentration versus time to find the slope for these. We could use it for this, because what happens is this is our y and this is our x. Slope is always equal to y over x, or rise over run. And here we see that y over x is concentration over time, and that's equal to k. But since these are exponential, what's going to happen is exactly what is the point of happening, which is that the rate's going to be different at every point. So there's no like one fixed way to solve for k here, because the rate does not equal k here. And therefore we would have to linearize it to find k. Sorry, my pen went kind of crazy. Same here. We need to linearize this if we're going to find k. So this is what calculus is for. They integrated the equations so that it could be linearized, so that we could do basic math to solve for k. So I'm going to show how you can rearrange these integrated equations and use them on these type of graphs to solve for k. And the reason we can do that is because the y-axes are different on all of these. So let's go look at that. So here we're just going to use algebra. We want to find k for this slope. And like I said, these are going to be the same, so zeroth order. So what we're going to see is if we want to put k by itself, we have to get rid of the concentration initial here. And then we're going to have the a final minus the a initial. And then that's going to be equal to negative kt. But we don't want kt, we would just want k. So we're just going to get rid of the t And now what you have is change in concentration over time is equal to negative K. So you just did the Y over X. So if a question gives you the final concentration and the initial concentration and the time, you can find K. Or let's say they give you K and the final concentration and time, now you can find A initial. And if you have a graph, you can just look and see if this was our, for example, our A initial, and then we came here to our A final. Maybe the question doesn't give you the actual molarity, the actual concentration, but you can actually find it by coming here and looking at your y-axis and being like, oh, there it is, there's the concentration. And then you would look for the time in between which passed for that to happen, which is like that. Okay. And then we can go to this one and we see that it's a little different. There's natural log, but it's the same mathematical principles more or less. So we're just going to get rid of this minus ln of the A initial. So we're going to have ln of the concentration final minus the natural log of the concentration initial. It's going to be equal to negative KT. And then it's your choice how you want to put this in a calculator. So let's get rid of the T real quick and show that this is now equal to negative K. So let's just put negative K here. So this is how we could solve for negative K. You can like put parentheses over this and then put it in a calculator. And as long as you put parentheses like that, then it should be correct. But if you know logarithm rules, then you can also use those. So that logarithm rules say that when you subtract logs from each other, you can do this, put them over each other. So that's how you can also put the top part in a calculator. It's really your choice, but make sure you don't do something like this. I'm not sure if that'll give you the same answer. I've never tried it and I've never heard that you could do that with logarithms. So that's why I'm making this video, to clear that type of mistake up. So similarly to the other one, what you will find is that maybe the question has no particular, it doesn't tell you what the final concentrations and initial concentrations are. It might just give you two dots and be like, this is A final, this is A initial. But now you have to see that, oh, okay, so this is, whatever is here is going to be equal to the natural log of the final concentration. Therefore, you can plug whatever number you have on the y-axis there here. Okay, so that's how that could work. And then you can play around as long you just can read the graph and play around. So let's try the last one. This is second order. So same principles apply. We're going to do 1 minus the sorry, I couldn't talk. So we're going to subtract the 1 over the concentration of initial. And we're going to do 1 over concentration final minus 1 over concentration initial equal KT. Now you'll see this is positive, so we're going to end up with a positive K, and the slope is also positive. We can see that. So let's get rid of the T. So this is what we're going to get in order to get K. So it looks complicated, but actually it's not going to be that bad. So what you should do is solve for this separately, and then what you'll see is that it's going to equal 1 over your concentration, basically. And then since that's over T, you'll see that 1 over M is going to be, because remember this rule, dividing fractions is easy as pi, flip the second multiply. We have a fraction here. So let's make it easier to visualize by putting T over 1, because any number over 1 is itself. So now I'm going to use my rhyme, dividing fractions is easy as pi, flip the second multiply. And I'm going to do this. Instead of dividing, I'm going to multiply, and the second one is going to be like that. So now we have the units for K. So I showed the units for all of them, I believe, unless I forgot the middle one. And then this one, what happened was when these natural logs are subtracted from each other, we lose the units. So it would just be 1 over time. Okay, and this is good if you forget like the actual units for k, because you can use the equations to figure them out. I think that's it. Last thing I want to say is be careful not to make a mistake, which is easy to make. It's doing this 1 over a final minus a initial and acting like that's the same thing as this. It's not. It's very easy to make that mistake because we use calculators a lot nowadays. Just put it in like this. And similarly, just be aware that that's not correct math. And so you have to be aware that if you have, if you are looking at a graph like this, let's go over that. Since this is the y-axis shows 1 over the concentration, what you're going to find is if there's 2 points along the graph, you have to remember that they're equal to 1 over the concentration. So if this is our A final, then it's not equal to just A final, it's equal to 1 over A final. So just be very conscious of what these y-axes are, and then you'll do great. You just have to use the rearrangement equations. Okay, so that's it for this one, and I'll see you guys later.